Hey everyone, welcome back, and today we're going to continue working on the advanced graphs questions from the LeetCode roadmap. So in the last video we finished the first 3 questions. Now in this video we're going to finish the next 3. So these graph questions are going to be a little bit more complicated than BFS and DFS. Instead we're going to use algorithms such as Dijkstra's topological sort or Bellman-Ford. So let's get right into it. The first question is swim in rising water. So in this question we're given an n by n, so a square matrix grid, where each value grid ij represents the elevation or the height at point ij. So then the rain starts to fall, and at time t, the depth of water everywhere is t. So we can swim from a square to another 4 directionally adjacent square if and only if the elevation of both squares individually are at most t. So essentially we can only move to our top, bottom, left, and right squares, and we can only move to them if their heights are at most t. And t is the time or the depth of water, but in our case we'll just care about it as the time. So, and also we can swim infinite distances in 0 time. Of course, you must stay within the boundaries of the grid during your swim. So finally, we want to return the least time until you can reach the bottom right square. And we start from the top left square. So in example 1 here, we're going to start from the 0 cell all the way to the 3 cell. And how long does that take? Well, we're going to have to eventually traverse to the 3 cell. So we can only reach 3 if the water is at least height 3 or the time 3 has passed. So 3 units of time has passed, we're able to reach the bottom 3 cell, and we've completed it. That's why the output here is 3. So in example 2 here, again, we start from the bottom left and we want to go to the bottom, we start from the top left and we want to go to the bottom right. So we want to find a path which minimizes the maximum element on this path. So essentially, we're starting from 0. We can either have 2 directions, the 1 or the 24. We see the 1 is slightly better, so we go to take the 1. Then we take the 2 because it's better than 23. And then we take 3 because it's better than 22, and so on and so forth. Eventually, we'll get this path that's highlighted here in blue. So now how long does this take? It's going to be the largest number on this path. That's the height of water that's required, and that's going to be 16 right here. So looking at the output, it's going to be 16. And we need to wait until time 16 for the water to reach a level of height 16, so we can cross this path without having to go through things like 21 or 17. So this minimizes the maximum cell on this path. And this is a square grid. So in this question, we can implement something very similar to Dijkstra's algorithm. So starting from the top left, we're going to look at the neighbors. Whichever one is lower, we're going to try taking that path. So because 1 is lower than 2 here, we're going to try going bottom first, and then try taking the 2 later if we're out of options. So in example 2, we're going to try taking the path 1 first instead of the 24. And we're only going to go back to the 24 if something later on is going to be bigger than 24. In this case, it isn't, but it possibly is. And to always find the smallest neighbor or the neighbor with the least height, we're going to use a min heap to keep track of the minimum one. So to start this question, let's say n equals to the length of the grid to make our lives a bit easier. And also we need to start a min heap. So min heap is a priority queue data structure that we covered before. And what this min heap is going to store is we want the minimum height. So let's actually just comment that. So it's going to be the height, and then it's going to be the coordinates row and column. So at the start, we have to start from the top left grid coordinate. So the height is going to be grid 0 is 0, the row is 0, and the column is also 0. So that's our min heap initialized. And now we want to visit its neighbors. And we want to visit them, all of them, eventually until we reach the neighbor, or not the neighbor, but eventually the target, which is the bottom right cell. So we can use a while loop, so while true, and eventually we're going to return once we reach the bottom right cell. So in this while loop, we're going to pop out the height, the row, and the column, and that's going to be using heapq.heapPop from the min heap. And after that, we want to make sure we don't visit this again because this is the best possible way of visiting the current cell. So we should have a visited set and added our current cell to the visited set. So we should create a visited set here. And what we do is we should add it to visited. So visited.add a tuple of row and column. So now suppose we reach the target. So if the row equals to n-1, which is also equal to the column. So we can actually do this in Python. So row equals to column equals to n-1. That means we're at the bottom right, in which case we want to return height. So suppose we didn't reach the bottom right yet, then we're going to have to try all of the neighbors of the current cell. So to get all the neighbors, we're going to set the 4 directionals that we can go. So we're going to create a directions tuple. So directions, this is going to equal to -1, 0. This means going up by 1, 1, 0. This means going down by 1. Or we can go 0, -1, going left by 1, or 0, 1, which is going right by 1. So to visit all of its 4 neighbors, we can do for dr, dc, representing the change in row and change in column in directions. So dr plus equals to r to modify our current row, and dc plus equals to c. So now we need to make sure dr and dc are in bounds, so it's not off the grid, because the question doesn't want that. So if 0 is less than or equal to dr less than n, and also 0 is less than or equal to dc less than n. And we also want to make sure that this hasn't been visited yet. So and dr dc not in visited. So if this is the case, we want to visit this neighbor. So first of all, we should add it to visited, so we don't visit it in the future. We're going to add dr and dc. And we should also set the maximum height. The maximum height is going to be the maximum of grid dr dc compared to the current height. So whichever one is higher, that's going to be the cost of visiting that cell. So, and then now we want to add this cell to our min heap, so we can eventually find it by popping from the min heap. To do that, we're going to use heapq.heap push. We're going to push onto the min heap, and then we're going to push the tuple of the maximum height paired with dr dc, the row and the new column. So now this is eventually going to find height, but if this is not the case, this question I think guaranteed has to have an answer, but if it's not guaranteed, then we want to return -1. So let's try running this. Cool, that worked. Let's submit it. Nice. So in this question, starting from the top left, going to the bottom right, at every iteration, we want to find the neighboring cell, so the 4 directionally neighboring cell, with the smallest height, because we want to minimize the maximum height on our path from the top left to the bottom right. So we're going to repeat this process every time. We're going to take the minimum height, or the neighbor with minimum height, and then we're going to push that neighbor onto our priority queue. So for all the neighbors, we're eventually going to find the path that is minimal, and once we reached the bottom right, so r and c equals to n-1, then we're going to return that height. This is the maximum height on this path, and this is the path with the minimum maximum height. So that's this question, swim in rising water. Let's move on to the next one. Foreign dictionary. So this question is actually a LeetCode premium question, but there's a free link on the LeetCode website. So instead of alien dictionary, we're going to have to do foreign dictionary. So in foreign dictionary, there's a foreign language, which uses the Latin alphabet, but in the order amongst the letters is not A, B, C to Z as in English. So for this new language, we're going to receive a list of non-empty strings words from the dictionary. And these words are going to be sorted lexicographically based on the rules of the new language. So we want to derive the order of the letters in this language. If the order is invalid, we want to return an empty string. And if there's multiple valid orders of letters, we can return any of them. And now here explains which strings are lexicographically smaller than other ones. So for example, if the first letter where they differ is smaller than A, then A is smaller. Or if A and B are identical, but the length of A is smaller than the length of B. For example, A is going to be AAAB, while B is going to be AAAB, RER. So in this case, A is smaller than B. Just like how English works. So looking at the examples here, the input is ZO. So in this foreign language, we know that Z comes before O. So our output is going to be ZO in that order. So in example 2, we have HRN, HRF, ER, ENN, and RFNN. So these are going to be in sorted order. So looking from the left to the right, we can see that, first of all, HRN is less than HRF. This means that N must come before F. And looking at the output, that is indeed true. So looking at the second pair here, HRF compared to ER, we know that H has to come before E. And indeed, that's also true. So comparing ER to ENN, R comes before N, that's right. And finally, ENN comes before R, F, and N. So E comes before R, and that's also right. So in this question, we're given the output H, E, R, and F. If there's multiple valid outputs, we can just return any of them, that's fine. So there's also cases where things in the input contradict each other. So if that's the case, we want to return an empty string. And that means there is an invalid dictionary input. So in this question, first of all, we know that we can return any of the valid orders. So that means we can topologically sort all the letters, given that we know the directions. So for example, in input 1, Z comes before O, so Z is a parent to O. So a valid topological sort for this case is Z then O. In this case, we can draw a diagram. So for example, we know that N comes before F, so we have, let's just do a comment here, N points to F. What else do we have? We have H points to E. We also have R points to N, and we also have E points to R. So these are the edges in our topological sort. If we put these together, we're eventually going to get the output. So knowing that we can do a topological sort, now we need to figure out all these edges, because unlike all the previous graph questions, we actually have to figure the edges out ourselves. So we can compare every pair of words in this dictionary to generate one edge, unless these words are the same or invalid. So to compare them, first of all, we can create a for loop for I in range len words -1. So inside this for loop, we're going to have two words that we care about, the word that comes before, for example, HRN, and the word that comes after, for example, HRF. So before, after, these are going to be words at I, and words at I plus 1. So now, to avoid getting indexed out of bounds, we can find the minimum length of these words, so mn. Let's say this is the minimum of the length of before and the length of after. So now if before from 0 to mn, so now we're comparing these two strings from 0 all the way to the minimum length. So if these two are the same, so if before equals to after from 0 all the way to mn, and the length of before is greater than the length of after, then that means we have a contradiction. Because the shorter length, if they're the same until the minimum length, then the one after should be longer than the one before. So if we have the opposite of that, so and len before is greater than len after, what we want to do is return the empty string in this case. So however, if we don't have a contradiction, then we can look at all the characters in the word before and in the word after until one of the characters differ. So if one of the characters are different, then we will figure out one edge in this tree, or in this graph. So for j in range mn, so in the minimum length, so we don't get an index out of bounds error, so if parent or if before of j is not equal to after at j, then we have a difference. So which means that the parent of the character at after is the character at j in before. So we can say parent after j dot add before j, and children after j, before j dot add after j. So notice we didn't actually create parents and children, so these are basically adjacency lists for edges to know how many children and how many parents they have. So let's create them. Parent is going to be a default dictionary, and it's going to be initialized to a set because we don't want to add duplicates of the same parent, because it's possible that there's words that generate the same edges for us. So we're going to use a set to avoid that easily. And now we also want the children default dict. So children equals to default dictionary, and this is also initialized to a set. So now we also need to keep a track of all the characters that are inputted, because for topological sort, we're going to need to start from a node with 0 in degree or no parents. So those are not going to have any parents, and they're not going to be in our dictionaries. So we're going to need to create characters, and this is going to be a set of characters for every word in words. So for every word in words, and for every character in word. So I think this is the syntax of how you do it in Python. Hopefully that works. So now we have the tree completed. We have all the edges. Now we're going to use these edges by using a topological sort algorithm. So in topological sort, first of all, we're going to create an in degree counter. So in degree equals to default, or we can just use a counter here. So for every character in the characters set, the in degree is going to be the number of parents they have. So in nodes with in degree 0 are the ones that we can possibly start with. So in degree of character is going to be the length of parent car, but we want to do this if and only if character is actually in the parent dictionary. So if character in parent, otherwise the in degree should just be 0 because it doesn't have any parents and it's a character that we can start off with. So now we can look at the topological sort DQ. So let's create that. So in topological sort, first of all, we're going to start with all the ones with in degree 0, and we're going to push them into a DQ, which is going to be a queue in this case. So DQ is just a double-ended queue in Python, and we can use it as a queue or a stack. In our case, we're going to use it as a queue. So inside this queue, this is going to be all the nodes with 0 in degree. And then we can take a look at all of its children and subtract 1 in degree from that one. So from each of the children, if any of the children have 0 in degree, then we should push it into the available DQ as well. And we can repeat this until we have a topological ordering of every single character inside this graph. And we also want to record this topological ordering, so we're going to create a string called answer. And whenever we have a character from the DQ that's popped out, we're going to add that to our answer. So now we can use our DQ. So while length of available is greater than 0. So while there's still characters inside available, what we want to do is we want to pop the first one out. So the one with the least in degree. So cur equals to available dot pop left. So to use it as a queue, we're going to have to pop from the left. Otherwise, popping from the right is using the DQ as a stack. So now with the current node, we want to add it to our answer. So ans plus equals to cur, because answer is the order of our actual alien dictionary. So now for every child in cur, we want to decrease that child's in degree by 1. Because we've already used up the parent, they no longer have to worry about this parent. So the number of parents is essentially going to decrease by 1. If any of their parents is going to be reaching 0, then we should push that into available, because that child is now ready to be added to our alien dictionary. Because all of its parents have already been added to the dictionary, then we can safely add the child. So now for every child in children of our current one, the in degree should be subtracted by 1, as I said. So in degree child should decrease by 1. And if we hit 0, so if in degree child hits 0, so if it's equal to 0, then we want to push it to the back of available. So available dot push, or it should be append child. So now we pushed everything into our answer, and this should be in sorted order. So of course it's possible that we are not able to cover everything in answer. So if the length of answer is not equal to the length of characters, so that means we must have hit a contradiction somewhere. For example, a edge that points from H to E, and another one that points from E to H. So if that's the case, then we'd have a problem. So we want to return a empty string instead of -1 because we're returning a string here. So in this case, we want to return an empty string. And if it's not the case, if we have a valid alien dictionary, then we want to return our answer. So return ans. So let's try running this. There's a raw answer with no output log. So I'm guessing there's a syntax error somewhere that caused it to crash. So possibly there's no counter, so we need to do collections.counter. Oh, we should break out after reaching. So before at index j, once we found a difference, we can break out of this. And another thing is that we actually did not initialize anything. So we didn't initialize the indegrees for example, for every character and indegree, and indegree items. So what we need to do is that if the indegree is 0, we're going to want to push it into available. So these are the characters that we can start out with. So if indegree of char equals to 0, or just indegree equals to 0, what we can do is push that into available. So available.append, and we append the character. So let's try running that again. Cool, that worked. So let's submit it. Nice. So in this question, we're starting out with an alien dictionary. So the first step in this question is that we're going to have to create all the edges ourselves. So to create the edges, we have to compare every pair of adjacent words because the left one is always greater than the right one. So we can do that. So we don't want to compare all the words. For example, you don't have to compare the first word with the third word because the order is transitive. So if the first one is greater than the second one is greater than the third one, then the first one has to be greater than the third one. So we don't have to care about the order because it's transitive. So now we just compare every pair of words that are adjacent to generate the map or the graph of edges. And once we have that map, we can just do a standard topological sort. So this question is a bit more on the difficult side, mostly because we have to create the graph ourselves. And after that, we just have to apply the topological sort algorithm correctly to be able to generate one of the answers. Because this question can have multiple answers, there could be multiple correct ways to do topological sorts. And we also have to remember to return 0 or return an empty string whenever we're faced with a contradiction or that something doesn't work out in the alien dictionary. So that's this question. Let's move on to the next one, which is cheapest flights within k stops. So cheapest flights within k stops. In this question, there's n different cities connected by some number of flights. So we're given an array of flights where flights I equals to from to price. So we're given the source, we're given the destination, as well as the price of each flight. So we're also given 3 integers, the source, the destination, as well as k. And we want to return the cheapest price from the source to the destination with at most k stops. And if there's no such route, we can return -1. So let's look at example 1 here. We have the source as 0, the destination as 3. So we want to travel from 0 to 3. And k is 1, which means we can have one stop, or we can stop at a different node, which is other than 3 before reaching 3. So for example, if we go from 0 to 1 to 3, there's only one stop, which is at node 1. And in this case, that happens to be the output, which is 700, which is 100 plus 600. So note that we could also go to 1, then go to 2, then go to 3. This is going to be 400, which is less than 700, but however, this is going to use 2 stops. We have to stop at node 1 and also stop at node 2. Because k is 1, we can only stop at a single node, which that means 700 is optimal with at most k stops. So looking at example 2 here, n equals to 3, we have some flights, the source is 0 and the destination is 2. K is 1, so we can have at most one stop. So in this case, actually taking this one stop is more optimal. So we travel 100, then 100 and reach an output of 200. So example 3 here, in this case, taking the direct flight is optimal. But also, direct flight is not optimal, but because k is 0, we can't have any stops, then we have to take this $500 flight. So in this question, a trick we can do is we can set the starting price of reaching every single destination, every single node along the way, to be infinite. And then we're going to set the price of the starting node or the source to be 0. So once we've set those, we can take a look at all of our edges here. So because only the source node has a price of 0, then we can relax these edges, or in other words, we're going to set the price of reaching 1 from node 0 to be 100. And then we can also set the price of reaching 2 from node 0 to be 500. So these two edges are relaxed, or in other words, these two edges are covered. So we know the price of the starting node, which is going to be 0, the price of node 1, which is going to be 100, and the price of node 2, which is going to be 500. Then we can do this again and again to determine a route with at most k stops. For example, if we do this algorithm again, then we're going to get the path from 0 to 1 to 2 is going to be 200. So if we do this algorithm twice, we're going to get a path of length 2, or in other words, a flight trip with at most 1 stop. Because we don't want to do that, we can only do this algorithm a single time, since k equals 1 in this case. K equals 0 in this case, so we don't have any stops. So we do this algorithm a single time, so we get the price at node 1 is 100 and the price at node 2 is 200. So then, because we're done, we did this k minus 1 times, or k plus 1 times, then we know the price at node 2 is going to be 500. So to code this up, first of all, we're going to have to set every single node to have a price of infinity. So in Python, for infinity, we can just do float of inf. So this is the maximum number Python can represent. And then prices is going to be a dictionary, or it could be a list in this case, because our locations are 0 to n. So we're going to use a list of infinite, and there's going to be n of them. However, there's one that's special, which is our source node, because the price to travel to the source node from the source node should be 0. So prices of the source node is going to be 0. So now after that, we said that we want to do the algorithm that I described k plus 1 times. Because if k equals to 0, then we still want to do 1 time because we can take 1 flight without any stops. If k equals to 1, then we want to do the algorithm 2 times because we can have 1 stop. Or for example, we'll go to 1 and then we'll go to 2. So that's 1 stop, or k plus 1 times. So for I in range k plus 1, we're going to take a look at every single edge here. So for from, to, and with the price, let's call that p in flight. So for all of these, if prices at fr, so the source, if this is not equal to infinity, or if this is actually equal to infinity, what we want to do is we want to continue, because that means we haven't unlocked this source yet, so we can't fly anything out of this from. So we're just going to ignore that for now. However, if the price at from is not infinity, then that means we can fly out of from to the to destination, which means that prices at to, this is going to be the minimum of the prices at from, so prices from, or actually it should be the minimum of the price to, or p plus price from. It should be fr. So after that, all we have to do is return prices at the destination, because we've done k plus 1 times, or we tried at most k stops. So after that, we can just return price at destination if prices at destination is not equal to infinity. If it's equal to infinity, that means we haven't unlocked the destination yet, in which case we want to return -1. So else -1. So however, with this algorithm, there's actually a slight problem, because at every range, or at every iteration I, we can potentially have flights going from A to B, then to C. So for example, if A has a price of 0, A is the source, and then we got a flight from A to B for example 100, then we get B is 100, and then there's a flight from B to C, which is 200. So if the travel time, or the ticket from A to B, is processed first before B to C inside this for loop, then we process B to C after. That means we've reached C, or if we've unlocked C in a single iteration of this big for loop. But however, this is taking a single stop. So this should take 2 iterations of our for loop. So we don't want that. We want to unlock B first and not unlock C, and then unlock C on the next iteration. So to do that, we need to keep track of the previous and the new prices, and we only want to update the price or the new prices after this inner for loop has finished executing. So we can create a temporary variable called temp prices, and this is going to be a copy of prices. So prices.copy. So now instead of comparing temp prices to infinity, instead of comparing prices, we should compare temp prices. So temp prices from, if this is equal to infinity, that means we haven't unlocked this target yet. So in this case, we haven't unlocked B yet, so we're not going to look at the ticket from B to C. That means we have to take another iteration to look at the ticket from B to C, which is what the question wants us to do. So instead of prices, we're going to do temp prices for all of these. However, the P plus prices are, this should be the previous price because we're looking at the price unlocked on the previous iteration. So after all of this, the inner for loop is done. Now we can set prices equal to temp prices. And the return problem, the return statement should still be right. We have returning price of destination if the price of destination is not equal to infinity, otherwise we want to return -1. So let's try running that. Cool, that worked. So let's submit it. Nice. So this algorithm that we're doing here actually has a name. It's called the Bellman-Ford algorithm. And based on how many times we relax all the edges, we're going to get a MAC path with the maximum length of that. So in this case, we can have at most k stops, so we can have a path of at most k plus 1 edges. So now using the Bellman-Ford algorithm, we're going to find the cost of the minimum path going from our source to our destination. So to differentiate the source, we're going to set the source to be 0 at the start. So that's the only node that's unlocked at the beginning. And then we're going to relax the edges to unlock all of the source's neighbors and their neighbors and so on and so forth until we've unlocked the destination. And because we're only doing this algorithm k plus 1 times, we're guaranteed that we have hit at most k stops. So that's this question, and that's the end of the advanced graph sections on the LeetCode roadmap. So thank you guys so much for watching. Hope you were able to learn something, and I'll see you in the next video.